All right, welcome back, everyone. Today is the last day of the bootcamp workshop. Thanks for all the speakers and attendees. For today, you may have noticed our schedule is very heavy on talks from folks from industry. That's by design because we wanted people to talk about the things that they're very excited about with applications, new trends, and hopefully it serves as a source of inspiration for those of you who are looking for exciting problems to work on or wants to develop new algorithms and such. I just want to point out that some of the talks, not all the talks, just a few of the talks will not be recorded. And the panel is not going to be recorded or live streamed. We just want to give people the ability to have opinions and be able to talk freely without, and so please pass the word around for people who are not in the room in case they are interested, but we're hoping to just watch the recording or just watch the live stream. OK, for the first talk, we have Daniel Ramage. Dan is my skip manager at Google. He was my intern host as well many, many years ago. He leads the Privacy Federation team at Google. Done lots of things, lots of cool, great things, both on the research and deployment side. So without further ado, Dan.
Thank you, Peter. So hi, everybody. I'm going to talk today about a bunch of different things representing a ton of collaborators. So this is collaborators who are acknowledged in the blog posts that I will be talking about. It's not the full set of collaborators on all the papers. And the bolded people are people from Google who are either here today or presenting later, like Brendan. Yeah, so I'll cover a little bit of what federated learning privacy have meant to us at Google since we coined the term in 2016 and as it's evolved over time. I think Adam Smith on Wednesday pointed out that the term has almost as many meanings as there are people who use it. So I'll give our most recent definition of what we think it actually means. And I'll talk about some progress on long-term goals as seen through a series of blog posts with the papers behind them. So these are all things that Google has described that we're doing publicly in production, not just the papers, which are linked from those. And I'll cover a few of the things that I think are the open questions that are really interesting and important to the field moving forward. So this is a Google Trends chart of federated learning differential privacy worldwide from 2017 to 2025 July. I stopped it in July because after July, the federated learning chart just goes bonkers crazy high. And I'm not sure what that is yet, actually. I don't know if that's like an AI slop thing or there's like some major thing going on in China that I haven't heard about. But that's this is kind of like, I don't know how meaningful this chart is. But if you say like, how for technologies that people maybe have a vaguely positive association of this is good for privacy and how that might deploy over time, we've seen a lot of growth in federated learning. And so what are some of the milestones here that I think are interesting? There was the first two papers in 2016. They actually came out of an internship project that Jakob Konecki was on during the same summer that Peter Kairuz was visiting. So Jakob was Brendan's intern. And Peter was my intern. And Peter and I were looking at local DP and seeing, like, can we actually do better in the local model? Because we wanted to have a sort of a memorization guarantee. And Jakob and Brendan were saying, well, we don't know how to do that for learning, but maybe we could like do something in this like distributed learning setting where we don't have DP. And so we explored those two branches. And that's a theme that'll come up time and again in the work that we've done at Google is we'll explore multiple branches. We'll realize like one of these can work, and we'll like double down on that and then try to get the kinds of guarantees we want building upon that. In 2019, we made this comic book, which was really fun. That was, I think it aged pretty well. And it was one of the things that I think helped make, along with some of the public communication from some of the big tech companies that they were using this technology, that I think helped get interest in industry for this set of technologies. And I think that was one of the drivers for why we saw a lot of people interested in this from not just the academic perspective, but from the industry perspective. And I think one of the papers that really kind of helped crystallize this field was the Advances in Open Problems in Federated Learning paper, which came out that year after a workshop that we hosted at Google in that summer that Peter actually organized, and some folks who are now organizers or participants in this workshop were there. And this was a time where we were just kind of getting a sense of how do we think about this field from an optimization perspective and a privacy perspective and a systems perspective. That was the core set of authors of the Advances in Open Problems in Open Learning, Advances in Open Problems in Federated Learning paper. These are blog posts that Google has published about the work we've done in federated learning. In the meantime, I don't think any of these were drivers in the spikes, but they're like a record of things that we did, including things that are mostly research into production. So most of these have something that's either an open source software or a description of a public deployment. And I'm going to give you today a tour of some of those. So when we started working on federated learning in 2016, the world was kind of moving toward on-device models, where we wanted to do a good job of working with data at the edge. And if we were going to do a good job of working with data at the edge, you might get a privacy advantage from that if you kept the data local, but then you wouldn't be able to improve. And so we wanted to build technologies that could kind of improve while keeping the privacy properties. And so, broadly speaking, all of the privacy technologies that we work on as technologists, especially people with kind of a research industry background, are aiming to kind of shift this privacy versus utility curve up and to the right. And I think if you look at a graph like this, you might think privacy means something like a lower epsilon, and utility means something like a better loss. But that's actually not really what we mean here. We mean something more abstract. This is why these are in quotes. Because utility can incorporate a lot of different things about how usable is the system, does it scale. Now that generative AI is one of the drivers of industry trends, a lot of utility questions are about how well these types of systems support and integrate systems that have an LLM in them, which is different than an optimization problem. On the privacy axis, we also were thinking, OK, the participants keep their data. That's pretty good for privacy, right? But of course, privacy is very multifaceted. And so I just wanted to include this quote from Daniel Solovey in this University of Pennsylvania Law Review article about sort of what privacy is. So it means a lot of things. It's a chameleon-like word used to designate a wide range of disparate interests, from confidentiality to personal information to reproductive autonomy, and often used to generate goodwill on behalf of whatever interest is being asserted in its name, right? So there's like a privacy washing component to claiming things are private. And there's also a lot of discussion about, like how can you take the concept of privacy and translate that to things that actually concretely reduce risks and harms to people, right? So I think these are essential components of what privacy means. So privacy is not binary, it's not scalar, it's a vector that we don't even know all the dimensions of. But when we think about a system like federated learning, we think that there's a set of dimensions that are really relevant that we've been iterating on over time. And this was definitely not our conception when we first started. But by 2022, we had published this kind of notion of what we think privacy means in a system like federated learning. So for the user, there's about transparency, auditability, and control. We need to make sure that users understand what's going on and can control things, of course. This is, for the kinds of platforms we build at Google, this is like based on whatever app or system is integrating the technologies. And then that platform, the one that we built within Google Research and currently powers all the production federated learning systems at Google, we want to have data minimization and data anonymization, right? So when we talk about a privacy property of the system, we want to talk about one of those more specifically. And data minimization kind of includes everything from a systems perspective too, like security, access control, TTLs, encryption. And anonymization I think differential privacy is one of the most relevant and operationalized gold standards that's gotten a lot of investment. But there's other flavors of how you might anonymize. Differential privacy might not always be what's appropriate for a particular problem. And one other dimension we think is increasingly important is that the privacy claims are verifiable, right? So either by the users or by external auditors or the service provider, that these claims aren't just made in a vacuum, say, hey, trust us that we're doing the right thing, but people can tell what's happening. So I'm going to do a quick tour of how we've thought about federated learning over time with a focus on that. And then I'm going to come back to verifiability, because that's a big focus of the work from our organization over the last couple of years. So OK, here's the canonical picture of federated learning, or a canonical picture of it. And note there's a couple parties here, right? There's the phones themselves, which have a user, which have their own data and their own ability to do some on-device training and model updating. And there's a big feedback loop between those devices and the server. And of course, this is all in the service of a model engineer, who's kind of the key audience of this technology. This is the person who has to use the system to accomplish a goal, like make the keyboard better. The usability of the system for this person is actually a really, really essential thing that's a little bit independent of, but complementary to the algorithmic perspective of how do you make the learning algorithms work. And of course, there's a system administrator who's in this picture too. It has to work well for them. And the final released model artifacts might go out to potentially many people. It could be public. So in the kind of canonical picture, you've got your local training data on devices. You've got your initial model parameters in the server. The devices are going to check in and see if they've opted in and they're available, whether they'll get work to do. For example, the current model parameters, and then you compute your updates, and you send those back across the fleet to compute a sum. But there's already a few data minimization principles that I wanted to point out here. Here's the first, right? So focus collection is one of them. The only thing that's being sent back is what's relevant for the current task. Now, this does not guarantee that those updates can't be used for some other thing. And so that gets back into the threat model. If you believe that the system operator is malicious, they might be logging those updates and trying to do something else other than the current task. But it's still a data minimization principle to say, hey, if I'm not going to collect more than I need. Sure.
So when you talk about only what's needed for computation, to what degree might that include what is needed by the engineer on the previous slide in order to interact well with the system, right? You talked about the usability being really important.
Yep.
And I'm just curious, do you include that usability as part of what's necessary?
Absolutely. Yeah. The question was, do you include the usability components? Yes, you do. And part of that, for example, is that metrics related to training are collected and computed along the way. Another data minimization principle is that these reports are ephemeral. In a properly implemented federated learning system, those reports are aggregated and discarded. But that's not something anyone else can verify. So we're going to come back to technologies to make that more verifiable. And then the aggregates are released to server side, which will sort of then loop. And of course, this is a third data minimization principle of only an aggregate release, so that we don't have individual data that's going away. So there's a bunch of data minimization properties for a federated learning system that's implemented correctly by an honest party. So typical orders of magnitude for cross-device federated learning that we've been looking at for the last few years is hundreds to thousands of clients per round. And for the models that we train on device, usually thousands of rounds to convergence in a few minutes per round. And of course, you can't control which devices connect, and that'll be really important algorithmically in a little bit. So productivity, right? The system needs to be usable, needs to be fast, needs to be debuggable. Otherwise, people won't use it. I'll give you one concrete example of this, which will come back a little bit later too. If your algorithm has a lot of hyperparameters, it's probably not usable, because if those hyperparameters are misset, then someone tries to use the system and it doesn't work, and they don't know why it doesn't work. There isn't an easy way to ground truth what those hyperparameters are if you can't set them on some offline data, and that just have it work when you translate to the online setting. And they don't know if the problem is in the algorithm or the problem is somewhere else, like maybe upstream in the way the data is being managed on these devices, right? So if it just doesn't work and they don't know why, it's actually a big problem. Anonymization. Of course, we would like to make a stronger privacy claim than just we did our best to minimize things. So what could an honest but curious adversary, so someone who has access to parts of this system and is looking at stuff, what could they learn by looking? And of course, the most relevant example of that would be these model parameters that are released to the outside world. Can you make a DP guarantee on those so that they don't memorize an individual's data? We'd like to, but we also might think about the admin access or the model engineers who has access to more intermediates. How much can we eliminate or reduce those information channels? And then sort of hardening and verifiability, right? What about an adversary who has deeper access to one or more subsystems, potentially corrupts them, causes them to collude, can do things that the system's not supposed to do? How do we protect against those? And this is where the verifiability part is really important. We want to build a system where we can prove to ourselves and to others that that can't happen, or that slices of those threats can't happen. So I'll talk a little bit about progress on some of the long-term goals in those categories. Here's kind of the first 4. There's going to be a couple others that I add along the way. Can federated learning and analytics be used productively? Can we make user updates not be visible to Google? Can we make sure the models don't memorize? And can we do that with higher quality? Those are kind of broken out as separate pieces. So they are productive. This is some of the technologies that have been publicly described for how Google is using federated learning. All of the keyboard models, a bunch of different components in the Android framework, Google Maps, health studies, hot word detection are all pieces of Google technologies that have deployed federated learning in production. And our current system runs billions of reports per day from Android devices around the world through this stack. There's actually multiple generations of the stack. So there's some on the older versions, some on the newer versions. Some are using DP, some are not, because this is a real production system. So there's a lot of complexity to that. But that's why and how it is widely used at Google. OK. So here is kind of one of those first goals. Can we make it so that the user updates aren't visible to Google? So that was one of the first questions. We say, hey, those updates actually encode a lot of the information, the raw data. Can we make it so that we can't see those? So in 2020, we introduced the topic federated analytics, which is kind of a peer to federated learning for just basic statistics questions. Other people call this federated statistics. In this paper, we introduced the practical secure aggregation algorithm, which was sort of the largest scale SMPC deployment at the time, which would let connected cohorts of devices be able to compute the sum of the reports, or for analytics, that would be sums of histograms, where only once enough participants had contributed to the cohort would you be able to decrypt the sum. And this was pretty difficult to get working from a systems perspective, but we slogged through and we did it. It's been running for many years, and I hope to turn it off one day because it's really a pain to run that system. In February of 2022, we released kind of a first paper, the blog post around training FL models with differential privacy. This paper did not use secure aggregation. This was a separate branch. And it was using the DPFTR algorithm. And this was the first production neural network, as far as we know anywhere, that was trained on real user data and announced with a formal DP guarantee. And there were some really interesting things for how that was able to happen. So first, of course, why anonymization, you all probably know, but like this slide of Brendan's, if you can correctly complete a sentence like Brendan McMahon's credit card number is, you have a bad model, even if it's got really good loss, right? This is a kind of thing that shouldn't be able to be memorized, and the model shouldn't be able to be queried in this way. And so for an ML perspective, there was, of course, tutorials earlier this week that did a better job than I will on talking about this, so I'll kind of skip over this. But the key point here is that we care about the setting where the adjacent data sets are different users for the primary case of federated learning when you have user segmented data on devices. So D and D prime are going to be all of one user's data is either included or not included. And we want to sort of make sure that the distribution of models from our training algorithm are statistically indistinguishable whether or not my data is in there, which will prevent things like one user's data, like a credit card number completion, being able to be included. Of course, credit card numbers actually get filtered out even before we train the model, so that particular example is a little bit contrived. So we did not use DPSGD for this result. But I'm going to show you DPSGD here in this picture because there's something really important. And this actually wasn't in Lydia's slides. So is number one here. Like, what are the ingredients you need? Number one, this is really essential for the DP guarantee, is you have to collect your batches of examples in the right way. And most of the DPSGD results assume that you're randomly sampling examples. Most production training infrastructure does not randomly sample examples. It randomly shuffles examples and streams them through. So one of the reasons that there aren't as many publicly announced DP models with privacy guarantees is that when you take a DP algorithm and you apply it within a training infrastructure that is not actually DP aware in its example selection criteria, you don't get a DP result. You just get something that probably has good privacy guarantees, but you don't know what they are. So you need to select and sample and shuffle your examples. You're going to clip. You're going to add noise enough to mask any contribution, and you'll do privacy accounting. And this is the independent noise kind of for each iterate model that we see for DPSGD. So that was too far. So in DPFTRL, this blog post was about DPFTRL as applied in production Gboard federated learning. One of the motivations for this was because of that sampling thing. So the DPFTRL algorithm allows us to get good formal DP guarantees when we can't randomly sample the examples or the users. And this was really important because DPSGD really relies on amplification via sampling. And you can't control which devices are talking to the server at any given time. They show up when they're ready. So we have to be able to take the devices that are available in the connected cohort. And the DPFTRL algorithm lets us do that with a formal guarantee. And so this was actually really essential for being able to get those guarantees with a specific epsilon delta. And of course, as we saw in the tutorial, DPFTRL estimates SGD iterates better despite actually having larger per round noise. So we were in parallel extending the work on secure aggregation. And we thought, hey, could we do something where we're doing DP and secure aggregation? Because we'd like to have the property that we can't see the updates and the output is DP. And so in March 2023, this is actually a year after the previous post, there was this really nice post from Peter and from Florian on distributed differential privacy for federated learning, where we're kind of combining these two properties. And the key idea for this was using the secure aggregation core algorithm, that's this magic summing box. Could we add shares of noise to the inputs before they went through that magic sum, such that the output after the sum was equivalent to computing the sum and then adding the right amount of noise for that sum? So you're going to clip locally, you're going to add a share of the noise, do a magic sum, and at the output, you'll get kind of what you would need for a noised clipped sum. But in this case, we did get some of the analysis to flow through to make a real guarantee, but the guarantee was much weaker than what we could get with DPFTRL, which also sent us on a path toward empirical privacy auditing as a way to make sure we were understanding the practical memorization protections we were getting. I don't think I'd link out to too many of those papers, but there's a really nice set of papers from Peter and other collaborators at Google about that kind of empirical privacy memorization to make sure that we're, even in cases where we have a large epsilon and delta, that we are really getting a meaningful privacy guarantee anyway. And that gap between what formal epsilon delta we could get with this kind of method and the one we could get with DPFTRL made us realize that secure aggregation wasn't going to be able to be the foundation for our work moving forward. We really needed to be able to handle the stateful algorithms well. So we're going to come back to that in a minute. But first, how can we get those high quality models that don't memorize with user level DP? So this is back to the setting where we're not doing SecAg, and we don't know how to protect the individual updates, but we want to have a really good model. So this was from February 2024. This was a post by Zhang Xu, who was at Google for a long time. I think he's currently at Meta, and Yanqiang Zhang, who's one of our collaborators in the Gboard team, where we announced some really nice results. So this is a bunch of the epsilons of the models we were training in with DP federated learning in Gboard. And you'll notice that these kind of are all over the place. And you might say, why are they all over the place? And the reason they're all over the place is because Gboard's a real keyboard. We can't have a keyboard that doesn't work. And the status quo baseline was without any DP guarantee. So what we're doing here is we're adding the best privacy guarantee that we can offer while keeping the utility of the keyboard good. And why do they vary so much? Well, that's a function of DP in practice being a three-way trade-off between privacy, utility, and the amount of data/compute. So some of these models were able to be trained longer on more devices with larger batch sizes, and therefore we could get much smaller formal DP guarantees. And so this was also the first production model we're aware of that had just a really, really low epsilon. Although even the high epsilon models, because of empirical privacy auditing, we know have really good memorization protection. And this is kind of like a set of the papers around the multi-year progress on making DPFTRL and the banded matrix factorization methods work really well in practice. So this picture on the left, I think we talked about sort of the lower triangular matrix, Toeplitz matrix structure that would let us do things and then and that you could optimize for it. This is actually a picture of what one of those optimal training schedules of a lower triangular Toeplitz matrix looks like for the actual training schedule that we use in production. And and so here's like a bit of the progress. This is for DP Stack Overflow language models with a high epsilon, which is like ones that are relatively high utility. And again, we have empirical epsilons that are lower than that. Their non-private accuracy for this data set. And this is the dashed line, the infeasible regime of full DPSGD, like, full batch gradient descent is in blue. There's a little bit of a gap there, which could close if there was enough data in this domain. But for this particular data set size, that's what the gap is. And sort of the methods that we worked on over time to close most of the gap. And there's actually another column in between here that just came out last year, which was added some in the central setting, added some amplification via sampling results into the middle. So we closed even more of this red to blue gap since this picture.
Can I ask, I mean, this is a Stack Overflow data set. Do you think these numbers are reasonably representative of what you're seeing in kind of deployment?
Yep. Yeah. Every time we close some of this gap, it is really meaningful. And you saw some of the epsilons on the numbers for the actual Gboard language model, so those are kind of comparable. This application, DP Stack Overflow, is picked to be similar to what we would see in a Gboard type deployment.
Thanks.
So kind of summing this up, there's a bunch of really cool stuff here. We also announced that sort of all the Gboard language models are trained with federated learning and DP, like now and going forward. So this is like a full transition of a super widely used application to a full stack of privacy technologies. And this is a great survey paper from Krishna and Jalash put it together, but includes a bunch of Google co-authors on it, including Brendan and Keith, Keith spoke on Monday, I think, on correlated noise mechanisms. So this is like a good overview for that whole family of methods. So, is there more to do in these categories? Yes, there is. But like broadly, I think the cumulative impact of this work was closing a lot of those gaps.
Cannot memorize language and don't memorize language? I mean, those guarantees don't say.
Oh, I'm not trying to do a semantic distinction there. I was a little bit sloppy in the two titles.
Okay.
Yeah, cannot versus don't. There's probably a semantic distinction, but that wasn't intended. Okay, but there's some challenges with this set of work, right? I pointed out one of them, which is that that gap between doing things with secure aggregation and doing things with a central aggregator remained and kept bothering us. And of course, right around this time was also when the industry was moving over to Gen AI models, where you have just a different set of assumptions about what's important, right? You're going to assume that there exists a very large foundation model in the loop somewhere, and that assumption means that you're no longer in the regime where you just have one model you're trying to update. You're doing something with respect to a giant model that there's no way you're sending over the network. And of course, we also really were nervous about being able to prove what we're doing server side for a couple different reasons. One of those reasons is that we wanted to be able to make sure that, like, first, it's not just the case that just protecting all the training iterates is enough. We really want to protect whole workflows. We want to be able to do things where we're doing something like a grid search of hyperparameters to the point about if our algorithms don't have hyperparameters, awesome. To the extent that they do have hyperparameters, we want to be able to do a grid search. We want to be able to kind of protect the intermediate results, even if we can't get a better formal DP guarantee at the end than we would have if we had released all the intermediates. We want to have that protection. So we want to be able to protect the whole flow and be able to prove to people what did we actually make visible at Google. And another problem with SecAg is robustness to Sybil attacks. We don't know how to make SecAg robust to Sybil attacks. If a targeted device comes in to that cryptographic protocol and we say, oh, that's the device we wanted to listen to, let's add 1,000 fake devices into the current round at the network infrastructure layer, that's something that we wouldn't be able to prove we weren't doing. It was just part of our threat model that's not something we do. So we wanted to be able to have DP algorithms that were robust to that.
Was that motivated by like an actual real complaint, or was this just you guys trying to do due diligence and do your best?
I mean, it's been pointed out to us that it's not in the threat model, and we've agreed with that. But I don't think, Audrey, do you think we got any like actual complaining about that?
We did actually. There was the paper by
Doug Leith. Yeah. So there's some work that was a complaint. Yes. That was looking at what we were doing in Gboard and pointing out things that we said we were doing publicly and saying that that was a privacy violation. And so I think it's a little bit hard to be super sympathetic to that because it's like, hey, but that's outside the threat model. Things like assuming Google is malicious and looking at the updates and then reverse engineering the updates and seeing that you can reconstruct the original data. And we're like, yes, we know, we published about that. And the criticism was, but you could be doing that. How do we know you're not?
Yeah, I mean, that was sort of immediately apparent in my world that was outside the threat model, but I'd say most of the people that I was talking to in the industry thought that was perfectly acceptable and not argument.
Yeah. So this leads us to some new long-term goals that we added a few years ago and have been making a bunch of progress on. Verifiably private cloud compute on federated data. I'll tell you what I mean by that in a minute. Verifiably private cloud compute for Gen AI and verifiably private DP synthetic data. These are some of the newer frontiers of what we've been working on. Okay, so what do I mean by cloud compute on federated data? I think one of the things I wanted to do is decouple three concepts. Federated data is like the distributed data set that's going to be owned and managed by those devices that are participating, or in the cross-silo federated learning scenario, it might be like the hospitals that are operating in a network. The compute is the distributed computation across that data. You can usually think of that as like a MapReduce kind of primitive with varying levels of security guarantees. And learning is the algorithmic setting on that computations on that federated data, as it's used mostly in literature. And so when I mean federated, centralized compute on federated data, I mean if we had a way to use, for example, confidential VMs, which is one of the solutions that we really have invested a lot in to compute on data, but with ways where we can make good privacy guarantees externally about how that computation works, that would be an instance of centralized compute on federated data. So we proposed in this TPS paper in 2024 sort of an updated notion of federated learning. I don't know if anyone will take this one, but our notion here focuses actually on the privacy properties and not on the mechanisms, right? So it would include cross-device federated learning as it's traditionally conceptualized, as well as centrally verifiable processing of federated data that's been collected for one purpose. So the entities collaborate to solve a machine learning problem, enable clients to maintain full control over the data and the set of workloads allowed to access the data and the anonymization properties for those workloads, and ideally in a transparent way. So here's yet another definition. So Adam's point that there's like one definition per practitioner, that's incorrect. There's multiple definitions per practitioner. So a bit of progress on how this is working in practice. So this is from March of last year. This was the first system. This system took about 3 years to develop internally, and this is the first time we talked about how it was used in production. And it was developed in parallel with the other stack. So this was a federated analytics application first. So it wasn't using learning algorithms. Think of this as the count histogram kind of setting, where we were really focusing on being able to make externally verifiable claims. So here's the updated cartoon, right? Devices are going to send encrypted data, and how that encryption is managed is super important. I'll talk about that in a minute. To be processed by open source software that's running in a controlled environment where that environment can prove to the edge what it's doing. And so that's a notion of we now have in one place the quote unquote federated data. So it's federated from the perspective of these devices maintain control because of the way the system works. But at the point of when we're going to run compute, you have centralized compute. And you've got some initial learning artifacts, and you can, inside the trusted execution environment, you're going to compute your aggregates. And if you want to have an anonymization property, you do that with DP. And you're doing that with DP in open source code, so other people can tell you're doing it with DP. We release it if it meets the DP guarantees that we needed to meet. And those guarantees are visible to all parties. They're visible to the client devices. They're actually visible to third parties who have nothing to do with the protocol, because everything that's running here is public in open source software and a public ledger that shows all of the workloads that Google could ever run. OK, so trust execution environment, TEEs. And this was used yesterday in Adria's talk. And of course, confidential VMs are like the virtual machines that are running in TEEs. What do they actually give you? Well, they give you confidentiality. So an executing workload state is secret, even from the root or the system operator. There's a big asterisk on that, which is that breaking TEEs is a hobby industry of people in the security community, and including this paper from Adria and some other Google collaborators that looked specifically at ways that you're not just breaking TEEs in general, but that you're using side channels that are sort of outside the TE threat model to be able to peek on the private workloads and be able to learn things from within those, which leads to a whole line of later work on algorithmic mitigations for assuming you're running in a TEE where someone could access your, for example, which memory pages you're hitting. What can you do with your algorithm to protect against that side channel? There's like a whole kind of little literature there that we're just starting up. The TEEs offer integrity. So the workload's execution cannot be unexpectedly altered, even by root or system operator, and verifiability. So processes like clients can communicate, get cryptographic proof of the workload identity. And so we're in this setting. There's different settings for where you might want to use a trusted execution environment. And the setting that we're in in something like Google Federated Learning is a little bit weird, right? Because we're both the hardware platform operator and we're the software operator. And so we want to be able to show that even if we're colluding with ourselves, like the user still doesn't have to trust us. And so a lot of the trust execution environments in like cloud providers that you might spin up a VM are not in this sort of harder threat model. So a lot of the stuff we do on a systems perspective is because these two entities at the bottom can be assumed to be colluding. We want to be able to prove, because of the properties of TEEs and the way we're doing our open source software, we can, and with a transparency ledger, we can prove that we're running a specific binary securely in a specific CPU, subject to whatever the current generation guarantees are of that trust execution environment. And there's a bunch of clever things with cryptography that we do that I'll talk about in a second that let us extend that sort of chain of trust from the first ingress point of upload all through the steps of computation to the final output, so that if you believe we're doing it right in the first step, you can see that we're doing it right from the first to the second, from the second to the third, all the way to the end. And so what we really want to be able to do is prove statements like, Google protects your individual data even from access by Google until it has been anonymously aggregated. Right? Like that's the kind of statement we would like to be able to prove to people. And to do this, some of the things we need to prove are, of course, the identity of the software. We need to prove that uploaded messages going into the system are going to only be processed by pre-approved steps. And by that I mean the device needs to, at upload time, say, I'm OK with this data being used for pipeline A, B, and C, but not D. If the system operator can add a new use, a use D, that is not something that was originally tagged at upload time, then they could do anything they want. They could add a new use D that just releases the data in clear text. So it has to be a pre-approved steps only. The correct order and the correct number of times is really important, because for a DP algorithm, you have to make sure that you're like not doing things repeatedly or too many times. The pre-approved steps have to preserve the relevant notion of privacy, like DP, and that you have to prove that only those steps ran and only the correct number of times. For example, one of the classic attacks you might think of would be to say, can I rerun my DP algorithm 1,000,000 times and integrate out the noise? You want to be able to prevent against that, because you're adding noise to protect privacy.
Sorry, I just got to add that running only the correct number of times inherently kind of required in most every one of these systems, whether DPs there or not, when you're doing TEE work like this, replay attacks are very dangerous and you need to prevent them. You need this property.
Yep, thank you. Agreed.
Tolerance makes that hard.
Okay, so here's how this data flow works. I'm going to talk through the blue and then the yellow. So on the blue here, devices compute a minimal set of messages for a selected set of tasks. They're going to, number two, they're going to fetch from this TE-hosted key management service, that's what KMS stands for. They're going to fetch keys that are signed by the TE-hosted KMS. They're going to encrypt the messages that they computed in number one and upload them, and they're going to tag it with an access policy. That access policy is really important because what that does is, so it goes into storage in encrypted form here. What that access policy does is it says, okay, we're gonna try to do some processing. So we're gonna start up some jobs in Google's data center that are gonna try to read this encrypted data. Are they allowed to get the decryption keys? Well, the answer to that is they have to prove their own identity to the key management service. And then the key management service says, hey, is this binary that's going to run next, was that in the tagged set in the access policy at upload time? If it's not one of those approved binaries, it doesn't get keys, so it can't run. And then this could actually involve many steps. It often does in practice. And then finally, a decrypted release. And that will also be a decrypted release. And that will also be visible in the open source code. So if you see the open source code, you can see what all the intermediate steps are, and you can see what the release thing is, and you can see that the release thing is the output of the DP thing. So if you believe that the DP algorithm is correct, then you believe that the output is anonymous. We're using AMD CVSMP for this stack, and a lot of the underlying technology for remote attestation that is based on is a different Google project called Project Oak. But there's a whole bunch of things in the confidential federated computations repo that actually allow this to work, because Oak is more about just like T's proving identity to each other. And then there's a verification flow. So this is, there's public instructions in the GitHub repo for how anyone in the world could do this. Step one is that the key management service binaries, they're endorsed and they're published to the transparency log. And what that means is that anyone can go to this transparency log hosted by Sigstore, it's a system called Record, and they can watch our keys, and they can see, okay, a new binary has been published. And then they can go to the source code, and they can build that themselves from the linked hash. The processing steps that we're going to run are put into an access policy, and the access policy is also published to transparency log. And from that, anyone in the outside world can see, hey, here are the sets of things that Google is claiming it could do. It doesn't mean we actually did them, but anything that we could ever run is going to be in that transparency log. So devices are going to check that the KMS and the access policy endorsements are present in the transparency log. That's actually done with an inclusion proof, so it can be done offline without actually talking to a third service. And then an external monitor over here could look at that series of endorsements that are made public in Sigstore and look at the corresponding open source code and build everything from scratch and see what those properties are.
Is anyone taking you up on that?
No, I'm going to come back to that.
Yeah.
Has anyone taken us up on the...
That is a monstrously hard problem to get someone to actually do that for you.
To do the looking.
Yeah.
Oh,
That's right. Yeah, I'll come back to the hard problem, some of the hard problems later.
Can I ask?
Yeah.
Just I don't know if you're going to talk about this, but you mentioned fault tolerance
Yeah,
being a challenge.
yeah. I'll come to that in 2 slides.
Great.
I'm going to skip this one for time. In a single T, you get confidentiality, integrity, and verifiability, but you don't get fault tolerance. If that T goes down, anything that's managed by that T is gone forever. So we built this stack. This is also open source called Trusted Computations Platform that makes a quote-unquote service T. So this is just a classic distributed systems kind of problem. It's a raft consensus protocol where if a TE goes down, a new one can come up and rehydrate state from the other TEs that are currently running. And this is the repo that has all the software we talked about today: TensorFlow Federated, Federated Computations Platform, Confidential Federated Compute, Trusted Computations Platform, a bunch more. This is all the stuff that we actually run in production. But it's not designed to be used by other people in production. This is the stuff that's necessary for Google engineers to do things in production and for external verifiers to check that it's correct. OK. coming back to those goals, I think that was kind of that first, like, can we do things with verifiable privacy? And can we do that for Gen AI data? We've got this paper toward provably private insights into AI use, which is sort of the first application and is sort of a Gen AI setting for this. This is also an analytics application. The application here is Pixel Recorder. It's an on-device recorder application that transcribes audio. And we were able to use the previous system to compute the first maps we've ever gotten at Google of what are people actually using this application for, which is really important for the product teams to know, like, hey, what is this working? Like, do people like this app? Are they using it? Are they getting the experience they want? How could they improve it? And maybe one of the interesting things here, this is a kind of a simplified version of the previous diagram, but there's two things. One is this is a practical application of an auto-tuned DP histogram. So there's no hyperparameters to tune whatsoever to get a DP result, which is one of those kind of key pieces we needed to make this practical. And the other point is that we're actually running LLMs inside the T to get the guarantee, to create things like the picture before. So we're taking those Pixel Recorder transcripts, we're uploading them, and we're asking a Gemma model to any question we want, like, hey, what are the topics in this transcript? The output of the Gemma model is what becomes the input to the DP aggregation mechanism. So regardless of what question you ask the system, you get the privacy guarantee, because the privacy guarantee comes from downstream of the LLM query. But it gives an incredible degree of productivity and flexibility to the model engineers, because they can ask kind of whatever question they want in an LLM sense, say, hey, like, what's going on here? If that output can be mapped into histograms, they can get an answer, and that answer has this really strong DP guarantee.
So what's the unit of privacy in this case?
User level.
User level?
Device.
But device, yes, device, not user.
So, okay, does that mean you get one query per device?
It's per. We do not. I'll come back to this as another thing. We do not do a global privacy budget across all tasks. And there's an important reason for that, which is that if you did that, you could only run one thing.
Yeah.
So I'm going to skip over this a little bit in the interest of time, getting to the open questions. But this was the first kind of flavor of like a taste of what synthetic data could do. That was a very kind of coarse notion of synthetic data, but we've been really interested in DP synthetic data as a way to enable a lot of downstream LLM applications, from insights to improvements. And like maybe if you did a really good job with being able to prove that you have DP synthetic data that's representative of your federated data, and that's what you release, now anybody downstream can work with that synthetic data without having to work with their system at all. There are some nice papers here. This blog post from July of last year was the first application of DP federated synthetic data. This one used kind of a fun little trick of being able to, we generated data with a public or non-private LLM, and then we rescored it based on the DP Gborn model, right? So we were kind of upweighting the things that look like what people type. But we want to be able to go to much richer things that can actually match the original distribution and not just be resampling from what the big model already knew, because part of the value proposition is like there's probably stuff that people are typing that the big model doesn't know about at all. There's a paper that we published about how do we do that in a computationally efficient way that I think is quite nice. This one is not yet running in production. This one's just a research paper, but.
Question about this point. I know, so in terms of like rescoring data that was generated some other way, people have also looked at the sort of Pate style architectures where you, which look a little different from like DP-SGD.
Yep.
And it maybe even makes sense to combine these in the sense that they seem to do sort of probably be good at different things.
Yeah.
In this project, have you explored any of these sort of other approaches to reweighting or scoring existing data sets?
I don't think we've explored that too much, but all the things we have explored are in this paper on synthetic data. But I don't think a combo of the reweighting and the Pate idea is one of the things we've explored. Although maybe someone else from Google knows, tell Adam at the break.
I think what you're referring to is private evolution.
Private evolution, is that what you said?
I don't know if you are you familiar with that class of algorithms where you like ask a public LLM to generate lots and lots of examples. You go back to your private data set. You try to compute weights on those examples. You take the weights, you go back to the public LLM, you tell it, these are the examples that I like. These are the examples that I don't like. They're not representative of my data set, and you iterate, you evolve.
Yeah, that's exactly right. The question is how do you do that? Like the sort of technical question is how do you compute the weights, right? And so you can imagine different algorithmic approaches.
Oh, yeah. So this has been explored.
Yeah. So. Right. So I've definitely seen some work on sort of fine tuning using this type of approach.
Yeah.
But yeah, again, the question is sort of like under the hood, how are you computing the weights? And they're, yeah, whatever. We can get into it offline.
Yeah, well, this is a recent survey of a bunch of methods from Google that are mostly in the centralized setting, but also the federated setting. And this is a very active area of research for us. So I haven't checked this box yet, but I hope to check that box soon. Okay, I'm just going to do like a quick tour of some of the many, many open problems we see, despite all the progress that I think we've made over the past few years at solving the problem that Google cares about solving in the federated learning space. There's still a lot left, right? So what does it really mean to prove an FL system is privacy preserving? There's so many different dimensions to that. A bunch of that is like the software correctness. What does the ecosystem of human and machine verifiers look like that's going to look at the source code? Do we have formal methods to check for correctness? Do we have LLMs looking at changes in the repo and flagging if something looks fishy? Like what does that look like? Composition of TEs and SMPC is another really big deal. We would love to have a system where if we don't need to have the data just protected by the encryption keys, that we can also have it protected by SMPC. We're also really interested in kind of like offering simultaneous DP guarantees under different trust assumptions, right? So we have one single system, but if you assume that this person is compromised or this system breaks, do you still have a DP guarantee? And what does that DP guarantee look like, and what does it buy you? And of course, algorithmic defenses against privacy leakage via side channels is another area that's I think really interesting. Under the model of like what the TEs protect and don't protect, can we make algorithms that can offer a good DP guarantee even if the system operator running that algorithm, they can't see everything inside, but they can see the things that are not protected, like which memory pages are accessed. This is a shout out to a Crypto 25 paper from Adria and a bunch of other co-authors on a successor to the SecAg algorithm that starts moving toward this idea of maybe saying, hey, like, how do we think about a full spectrum of things that are cohorts of connected devices or non-colluding servers or TEs or non-colluding servers running in TEs or maybe in different geographic jurisdictions so that you have to compromise both the government of Switzerland and the government of the United States if you want to be able to access the raw data. Like, what does it look like to have this kind of richer ecosystem of distributed trust? There's no what?
There's no HE on this slide,
No.
for example.
Homomorphic
The previous one.
encryption.
Sorry, yes, homomorphic encryption. Apologies. And I have my opinions why there might not be, but a lot of people have assumed there always would be once this finally started happening. And I'm curious if you could speak to maybe why that's not there. It's just not part of your threat model.
That's a good question for Adria to answer. What do you say, Adria?
Yeah. So this goes back a little bit to the tutorial. Think of multi-party computation as a definition, okay, and not as a tool. HE is a tool to achieve that definition. So when you see SMPC, don't think of secret sharing. Okay. Think of simulation-based security, algorithmic guarantees, reductions to well-studied cryptographic problems. Under the hood, you can use lattice-based cryptography and therefore homomorphic encryption as a tool to achieve that definition. Try to move away from, am I using HE, am I using MPC? This is the analogy of thinking of Gaussian noise as DP. Adding Gaussian noise is not DP. DP is a definition that you can achieve by those means. The same, and in fact, lattice-based homomorphic encryption underlies that Willow protocol to achieve, simulation-based security. So yeah, I think this is something I see often, like sort of confounding the method with the definition. And to DP, it happens sometimes. Sometimes people think of adding Gaussian noise as doing DP. Yeah, so I think that's a bit of the confusion there.
Yeah, and then you get that email from the executive and you spend it all day trying to assuage their fears.
Yeah, I've seen it in many high-level summaries, like the HE, MPC, DP, what do you want to use? And I think we have to go beyond that.
So
Beautifully, yes.
I'm gonna. I have just a couple slides that I would like to show you, even though we're 1 minute over. I'll just note that these kinds of things don't work when you need to take the encrypted data and run it through an LLM, right? These are scenarios where you can do something like a homomorphic sum of your inputs. So like things like where the histogram bins can be computed at the edge, or a gradient can be computed at the edge. There's many open questions on anonymization, right? So can we make epsilon and delta meaningful in specific instances? Is there a way to connect them to real-world privacy threats in a way that's less like specific use case by people every time? Is there something cool to do with LLMs that we could like make that more scalable? Improved automated empirical privacy auditing, closing the gap between empirical and theoretical results. Multi-ownership attribution and accounting. So that's really important for scenarios where there's a sender and a recipient. DP-like guarantees when we don't know the owners of the data. So all the scenarios here assume that we know whose data it is in order to compute a neighborhood definition, but that's not often the case. Like take everyone's all the photographs in the world. There will be human individuals in many people's photographs, but they're not labeled. So like what does that look like? Can we beat the union bound when the workloads are known? Right, so if you get, this is to the point about cumulative privacy budgets. If you're running 5 different things, you have a trivially bad union bound. You say, oh, you have no privacy because you had 5 things with epsilon equals 4. So like privacy out the door. But it's not a generic 5 things with epsilon equals 4. It's these specific 5 things. Like we published exactly what we did. Is there a real attack against those 5 things? Yeah, in ongoing way, partitioned ownership and of the data with ongoing data obligations, that like different parties might have different data requirements and needs over time, and like how do you build a system that can honor those? This is just a picture from a paper that actually Adam was on this one, on sort of this multi-ownership contribution bounding stuff. Utility and productivity, right? I mentioned this, like if your algorithm is dependent on hyperparameters, it can't be used in production. It really can't, unless those hyperparameters can be fit on something that is already public and they translate to the private domain. Because if it doesn't work with the wrong hyperparameters, people have no idea why, and they think the system's broken and they don't know how to fix it. FL algorithms that assume a pre-trained foundation model and scale to meet the available compute. That DP synthetic data paper I didn't talk about is one of those. A lot to do with DP synthetic data. Other things that are applicable in the LLM world that you might have heard a little bit from Sean on Monday, like federated LoRa's or prompt tuning and personalization, are all areas that are super interesting. And a broader perspective. The intersection of these privacy definitions with actual legal, regulatory, and social perspectives is fuzzy or can be made crisp in certain instances, but isn't widely communicated and understood. Scenarios where we have agents who are reasoning about sharing individual pieces of data is another thing where DP doesn't really work. And there's a lot. Actually, our group is doing a lot of really interesting work there. I didn't talk to you at all about today. But you have this other idea of anonymization that journalists use, which is they take a story, and then they anonymize the sources, and they share the story. That's not DP. That's a social judgment about what is the relevant piece of data that needs to be privatized. What does that look like? So that's my talk today. Thanks so much for the great questions. And this is the blog posts, and the blog posts link to most of the papers. Yeah, that's it. Oh.
So I have 2 questions. So, oh yes, the mic, yes. Thank you. So first of all, this was a really nice talk. I really enjoyed it very much. It's quite impressive, the amount of work that you guys have, built up over the years. It's really impressive. So I have 2 kind of, questions. So first of all, my impression is that these days the smaller models are all distilled from the bigger models, or at least from what I've seen, right? You train a really big model on a whole bunch of stuff, and then you want a small model which is highly performant. You never train it from scratch. You just kind of do the distillation. So have you thought about, privacy preserving approaches to that? Because the prompts there that you give to distill and then distill the result, right? There might be some interesting privacy challenges there. The other question is a bit of a comment than a question. I don't know if you have seen, Anthropic had this survey of why do people use Claude, and there were these journalistic stories, and they were like half of them were de-anonymized. So that's a word of caution over there.
Oh, yeah, what's a good reference? I've seen the original Anthropic paper, which
Yeah.
costs-
So I think if you look for Tianxi Li is the person who did the de-anonymization. So if you look for Tianxi Li on archive, there's an archive report on
Okay,
this.
thanks. It's a good paper.
Yeah, those are great questions. So to the first question, I think that is one instance of the whole family of like, what do you do when you assume there's a foundation model? How does that change things? And we have lots of ideas and have tried some things, and we're trying more things. So I think that's right at the frontier. I'd love to chat with you afterwards about what ideas look promising to you. Sean in the room also has been thinking about that a lot and spoke briefly about it on Monday. For the Clio world, there's a paper and a separate blog post from another privacy team in Google Research about a differentially private variant of Clio that we released. Peter was an author on that paper, and I think Peter has also done some other flavors of showing the weaknesses of the non-DP variant of Clio. What I showed in the differentially private insights into recorder use, that one is, we think, a much better sweet spot than what Clio did. Because Clio was like, let's just kind of do some clustering and summarization and like hope that is private. And what we're doing is that paper is we have a bulletproof DP guarantee and then complete flexibility for the analyst before the DP guarantee. And I think that's just a nicer setup, but they're slightly incomparable, like which kinds of things you can do. Peter, did you want to add anything to that?
All right, we're going to take maybe 10 minutes of break. We can keep chatting, and please be back in 10 minutes.